Okay. So, dear participants, we will move forward to our next session. So, I request our student Anushka to please introduce our speaker, Sajeeth sir.
So, good evening, everyone. It is my pleasure to introduce our expert speaker for today, Mr. Sajeeth Kumar. He completed his bachelor's degree in mechanical engineering from PSG College of Technology between 1999 and 2004, laying a strong foundation in core engineering. With over 23 years of experience, Mr. Kumar has built a career that spans both academia and industry. Since 2018, he has been associated with BITS Pilani as an adjunct faculty, where he has been actively involved in developing experiential learning programs in automotive engineering. This includes creating e learning modules on engine design, simulation, and testing, as well as setting up physical laboratories that give students practical hands on exposure. Currently, he is the head of R&D EV Skill Lab, SkySkill Academy. His work bridges the gap between education and real world engineering challenges, preparing both students and industries for the future. Today, he will be speaking on a very relevant and forward looking topic: digital twin laboratories, transforming EV engineering education through virtual physical integration. So, with that, let us all welcome Mr. Sajeeth Kumar.
Hi, good evening, everyone. Hope I'm audible. Right. So,
Yes, sir, you are audible, sir.
thank you
Hello,
for
sir.
that. So, I just thought I'll show my face here, and then like been a long day, so probably switch off the video while I speak. So I'm Sajeeth. I'm what I would like to call myself as a cross-domain engineer. So mechanical engineer with no formal training per se in electronics and software, but I've been kind of working in those convergence domain areas for quite some time. So I'm going to kind of be sharing some of the experiences that I've had working in the industry and working at BITS Pilani. Coincidentally, though I say that I do have academic background with my teaching at BITS, the thing is I teach in the work integrated learning program, which means my students are again working professionals. Um, so yes, my experience with the fresh graduates or engineers is a little limited, but I think I can probably take some freedom here in claiming I do have experience in both sides, right? And I mean, happy to see Ramesha ji here as well. So, been following him for a long time on LinkedIn as well. And something which he mentioned kind of struck with me. So, the skill gap which is present in the industry, and how do you basically address it, right? So, I would like to probably like take this by using a whiteboard. I'm not big on slideshows and stuff, so I'm just going to be since I'm going to be sharing some of my thoughts. You have the whiteboard visible, right? Yes, right. So I'm going to be using this. So hope that's okay with everyone, right? So it's more of an informal way for me to present what my thoughts and learnings are. So let me start this by talking a little bit about the problem statement, right? So we have a lot of people talking about the industry skill gap, industry academia skill gap. But when you really look at it, right, so what exactly is this skill gap that people are talking about, right? So this is something I would like to dwell a little bit of time on, right? So to really understand what the skill gap is, and then kind of like as educators, probably try to present a vision about how we could use digital twins, machine learning, vibe coding, LLMs, and all this AI and stuff like that. How we could use this to build out modules for ourselves, build out better learning tools, build out better student learning experiences to speak about, right? So that's going to be my agenda. 1.5 hours is the time I have. So, right, I would probably take under an hour to go through this. So, the first part of it, which is actually the skill gap. So now when we speak about skill gap, the understanding is that there are various ways in which this manifests, but the primary thing is we tend to think skill gap is basically lack of knowledge, right? So this is one perspective that a lot of people do kind of like Okay, someone has raised a hand. So do we stop for questions right now, or do you want me to take it in the last? Jatinji, if you're there, okay, let me continue with it, right? So some of the the ways that people do look at it is, the first one would be a lack of knowledge, right? This lack of knowledge were to be true, right? If this is basically what is causing all the problem with people, right? Then automatically the next the solution which comes out from this is for people to immediately go and probably pitch what we call as our e-learning modules, right? E-learning modules. This is the kind of the thesis that the edtech companies came up with, right? So during the COVID times, I think we got latched onto this thing where people thought that the skill gap was basically down to the lack of knowledge, and the only way you can fix it is by giving a lot of e-learning courses. There are a lot of companies which do offer it, but I personally found that the skill gap is not just the lack of knowledge, right? So again, this is from the work that I do consulting with companies. I do staffing services, so I recruit people. Maybe not so much in the last 1 year, but the years before that, we would probably be staffing, I mean, probably be recruiting about 50 to 60 people in any quarter. We would be deploying them to tier one companies, automotive OEM. So I do have some kind of like insight into what exactly the skill gap is. So yeah, so one understanding is there's a lack of knowledge, so which is basically where we think we'll need to put them through it. And the second one is we kind of like would tend to think that there's also a lack of practical exposure, right? And the moment you call something lack of practical exposure, what comes to your mind, right? So the next thing which probably comes into your mind is, hey, okay, let's put up some labs, right? Let's put up some COEs, and hopefully these labs and COEs, they are supposed to fix it, right? So this is the second postulate which people have. Now, what I am trying to build is, I'm not saying it is wrong. I mean, I'm not saying like these don't help. They do, of course, help. But what I'm saying is, these would probably be the tip of the iceberg, right? Because as far as I'm concerned, anything to do with knowledge or practical exposure or anything to do with this, these are some things which are easily fixed with just small curriculum changes, right? So maybe there's a university which has not updated its curriculum, something like that, right? There's a very small change which is needed. It is I would say it is probably something like a process change, right? It's not something which is a very deep problem or something. But what actually is the problem? If you kind of like move on to the other side here, the same skill gap, but if you move on to the other side, what I see as major problems, right, would be the first and foremost problem would be a lack of application skills, right? Let me kind of circle back to it in a bit, but what I would say is a lack of application skills. You have knowledge, you have a lot of practical experience, you have had amazing labs in your college, but you still have a lack of application skills. I'll dwell some more time on it, right? And the next most important problem would probably be a lack of knowledge of industry processes, right? So this is something which is, I mean, a lot of you would agree with me. Whenever you have an industry, you kind of live and breathe with your processes. It could be your IATF, it could be your ASPICE, your ISOs, whatever, right? So irrespective of whatever industry that you're working in, whether it be manufacturing, embedded software, electronics, hardware, pure software, ITES, AI, ML, whatever it is, you are going to have a lot of processes which are involved in it. And what I primarily see as a deal breaker for a lot of these companies is people don't understand the industry process, right? So you could also go one step further, and you could probably say industry techniques and processes, right? So maybe there are multiple ways in which you can do a same process, and industry follows a different way. You don't probably do that in the college, and you'll need to kind of adapt for it. So a typical example could be, how do you write embedded code, right? A regular way of writing embedded code would be to you have a problem statement, open up your IDE and start typing out. But that is probably not how the industry expects you to work. They expect you to do some systems engineering. They expect you to do some requirements gathering, analysis, and then probably get in, right? ASPICE, that's what it prescribes. ISO 15288, your systems engineering prescribes the same processes. So as far as I'm concerned, the more critical gaps that you should be looking at would be on a lack of application skills and a lack of industry techniques and processes. So you could think of it from an electric vehicle domain. So let me just, because I made a pretty big claim, I perceive. So let me kind of like give a little example to kind of justify why I say this, right? So now let's say that you are in an EV industry, and someone is wanting to kind of like probably like do a platform engineering, right? They are now trying to select what motors do we purchase, what is the gearbox that we purchase, how do we basically go about with it, right? So I've had some little experience working with some of the startups in Tamil Nadu, EV startups more specifically, and I've kind of seen them firsthand how they do this, right? So for them, a platform engineering is more about going and finding the right vendor, figuring out what motors are present, right? So there's just one way that you go get a motor. He gives you a gearbox, and he also probably gives you a controller. And the next thing that you do is you start integrating this, right? So this is basically how the whole so this is how the whole process actually works for them. There is nothing else which starts off with it, right? And at least the startups I've seen, these startup founders don't have industry experience, right? And they think that following an ISO process or a standard actually slows them down. So they think that if you are a startup, you'll have to jump in and go and start building it out, and you get the product, and then you'll get funding, and then you can go back and do some more process engineering. I think that is basically where the whole the gap comes up. So the processes are not there to kind of slow you down, but they are more like a way of making you think, right? So what if there could have been more than one particular motor which could have worked for you? What if there was a different calibration which you could have done on the controller? Are you checking it, right? Do you have any kind of a means to systematically approach this? Do you have anything of that sort which would allow you to do it, right? So this is what I call as a lack of probably like industry technique knowledge or an industry process knowledge. So not just this, right? So you take a person, you put him into probably something like a DFMEA exercise. You ask him to do a DFMEA document, or ask him to do some kind of like failure analysis, root cause analysis. They are not going to understand how to do it. They're not going to understand how it is to be done, which is kind of something what industries would look for when you're recruiting some junior level graduates, right? So that's on one thing. Now, the bigger problem, like I said, is lack of application skills. Now, what exactly is lack of application skills, and how do we kind of like really get to the bottom of it, right? So now there is something which we have already seen, right? So we probably like are pretty well versed at using it. Let me just anyways get a picture of it and put it out here, right? So this is Bloom's taxonomy, right? So I guess as educators, most of us are familiar with it. One point of time or the other, we have done it while we prepare, at least when we prepare the course objectives, program objectives, right? So we've been through this, we kind of understand what it is. So now what I'm trying to put focus on here when I say lack of application skills, so it's basically to the fact that our current a very good number of people they kind of lack skills on the ability to probably like create, or ability to probably like evaluate and develop a come up with a decision or something, right? So what I'm trying to say is that we kind of do not give them enough opportunity to develop their HOTS, which is your higher order thinking skills, right? So we do not have a lot of opportunities for this. Now I know it is a pretty big statement to make, right? Because if you take your course level handout, you're going to see that we are in fact promoting it. We say that we have sufficient inputs which we have given and stuff like that. But somehow a lot of our programs still fall short on this one particular aspect. So how exactly can we do this, right? How exactly can we build it up? I mean, please remember, I'm still trying to build it all up to kind of come in here, right? So which is how do we transform EV engineering through virtual physical systems? So to reach there, I'm just still touching upon the fringes. So please stay with me on this. So the thesis that I'm trying to build up is, I'm saying that higher order thinking skills are lacking in a lot of programs, and the reason why this is lacking is because we cannot truly afford to kind of give our students, let's say we have I mean, in bits we have about 600 650 students in every single semester, right? So there's the WILP department, so there's 650 students in the MTech automotive engineering and automotive electronics, and I'm pretty sure that other colleges you're looking at similar numbers. So now imagine for a minute if we decide that, okay, let's take this problem, right? Let's take this problem of platform engineering, motor plus gearbox, right? Let's take this and let's probably go and ask our guys to do it here, right? So let's say that we've decided, no, we are going to fix it. We are going to kind of make sure that our students are going to get all the higher order thinking skills exercises they can get, and we are going to ask them to do a platform engineering. We're going to ask them to do a motor selection, a gearbox selection. We're going to ask them to do it. How do we make this happen, right? One way that we can actually do is we can ask them to do it in MATLAB, Simulink, and stuff like that. There are a lot of 1D modeling packages which are available, but it kind of like still kind of lacks that the physical connection which a student might expect. And for a student, at least, he is not wanting to go and spend time modeling a motor or a gearbox, but rather he wants to select a lot of different options. He wants to kind of like imagine himself being someone who's working in an industry, maybe say something like Tata Motors or Mahindra or something, and he wants to kind of play out that kind of a fantasy, right? So now how do we offer them that? That is the question, right? So okay, let's come to the how, but why can't we not afford to offer? So the question about why we can't afford to offer it, it basically stems from a single fact, that whenever a student works on a motor or a gearbox, you ask them to integrate it, you ask them to go test it, your capital investments will become consumables, right? I've seen it happen in our companies. So we get new engines, we give it to our the students, trainees who come down. We tell them, okay, you're going to learn disassembly, assembly, work on it, learn, and after 2 batches, 3 batches are through it, there are at least 10-20% of bolts which are slipped. There are probably like head bolts or something which is lost. They kind of like the pistons don't fit anymore. The piston rings are damaged. I mean, it happens. That's kind of like how our students work. So it is kind of almost impossible for us to kind of like hope that we could keep doing it for 600 people, 1,000 people. If you're trying to do it at scale, just imagine the scale that you're talking about. So this is not something which really works out, right? I hope everyone agrees with me on this, right? So capital investments are not supposed to be consumables. We can replace, replenish every quarter or month, but a capital investment, that's what most of your lab equipments would be. We cannot do that, right? So what we end up doing is we tell the students, right? This is something which I love talking about a lot. So we tell the students, to basically perform experiments, right? So this is what we tell them. We tell them, okay, you can perform experiments versus experiment with, right? So basically you are telling them, you just follow a certain steps. We are not going to allow you to do anything and everything you want to do with it. We're not allowing you to do all of those things. We only want you to do it step by step. Switch on the motor, set the load to so much, set the RPM to so much, measure the torque and power and current. Write it down on a notebook. That's it. Your experiment is done. Write your inference, write your summary, you move on. And for some reason, we tend to think this can actually help us with the higher order thinking skills. But I basically think that these are only like, kind of supporting your lower order thinking skills. So they remember how to do a process, they come back, they memorize, they come back, they just repeat the same thing, and that's what we are testing, right? So this is my own thesis. I would love to hear your opposing views on it. Would be happy to kind of like take your views on it, but this is my view on it, right? So the first thing is, how do we approach it, and what are the problems that we face, and why is it that we are not able to hit the higher order thinking skills? That's the first part. Now, the second part which comes in, yeah, maybe like I can just take a very quick break here. Um, so to kind of like ask if there's any questions here, because I think I've given out too much of, I don't know. I don't know if it's controversial, right? Statement. So do you want me to stop for any questions?
Yeah. So dear participants, if you have any questions, you can write in the WhatsApp group right now. Actually, chat box is not working properly right now, but we are on it. So if you have any questions, please write in the WhatsApp group. Yeah, actually, I got one question. Actually, the one participant asking is how the digital twin supports the remote or online EV education.
So I'll probably, I mean, that's what I wanted to know. So before I speak about it, I think I should show you how it would probably work. So then probably
Okay.
it will help anchor this. Okay, so now at least you know what is lacking, right? So I'll probably go ahead and show that. I'll do that. I'll do that.
Yeah.
Any other questions, or can I just start?
Yeah. Another question is there that can digital twins be used for EV charging station simulations, and if how we can do that? Yeah,
Okay.
that's the second question for participants. Yeah.
Okay. So I'm just gonna stop presenting for a while and at my entire screen, right? It's still visible, right? Okay, right. So,
Yeah.
so the question was about what exactly the product, I mean, the platform is. How does? Uh, okay, let me probably write it down here, right? So the question specifically were revolving around digital twins, right, and virtual labs, right? Um, Learning and development via virtual methods. Okay. So let me probably put up this question. See, I'm at home. I'm not in the office. I'm unable to show you the products per se, but I can probably show you the front end of it, right? So now, please bear with me. Let me probably like just take you through this, right? So now, what do we mean when we say virtual physical integration? Okay, so that's what I'm probably going to be touching upon right now. So let me show you how a typical lab equipment usually looks like. Let's take batteries or motors are simpler. Let's start with motors. We can probably go with batteries. I'll show you batteries charging. I'll probably talk about charging as well, right? So now suppose you have a motor testing equipment, right? So you have a motor. So usually you would purchase either a BLDC or a PMSM motor. PMSM being slightly more expensive. Let's say we have a PMSM motor, and this PMSM motor is usually connected to a dyno. So depending on how much you are spending, you might probably end up buying a rope brake dyno or a hydraulic dyno, or if you are spending a lot, upwards of 30 lakhs or something, you probably get yourself a eddy current dyno. But let me just say that there is a dyno here, right? And now you have loaded your motor to the dyno, right? So this is the motor dyno setup that you have. Now this is the physical, right? So think of this. So this is your physical realm. Now, what exactly is your student doing, right? So let's say that you have a student here, right? And what exactly is this student doing with your equipment, right? So this student is most probably, right, in most of the cases, this student's interaction with this equipment. Of course, there are going to be some dials and some gauges, something which he does, but this student's interaction with this particular equipment will most probably be via a control panel, right? I mean, please correct me if I'm wrong. If you do have a different way of approaching this, please do let me know. But the way I see it, you have a control panel, right? So I'm not talking exactly about what this control panel is, how it looks, or anything of that sort. But let's just say that there is a control panel, and any interaction that the student has is only via the control panel, right? As in, if not for the control panel, the student does not actually have a way of retrieving information from the lab equipment. Okay, so what information are we talking about here? So the student is probably going to be able to look at your motor RPM, right? Your torque, you're going to be looking at current, uh, voltage. At the best, these are stuff that you would look at and probably calculate your power and other things and all, right? So this data is either available as a digital readout, or there is a graph, or sometimes you can download it as an Excel sheet or something like that, right? I hope everyone is with me on this, right? So you're all aware of this, you are with me on this. So now my question is, what if I say I'll give you a more advanced control panel, right? You don't have to stick with this age-old control panel. So what if I can give you a more advanced control panel? When I say a control panel, I mean something very old with some, dials and meters and something like this. So now I'm saying I'm giving you a modern day control panel, right? Which has got a TFT LCD, right? Something like that. A little bit modern. Not that we cannot work with here, but let's just assume that it's a little bit more modern. It's like a computer, you have a data logger, you're able to collect it. It's a little bit modern. Just humor me for once. It's not that you cannot work with a typical control panel. You can, but I'm just trying to build up to something here. So now, can someone tell me, you as a student, how do you know that this motor RPM, torque, and current values are actually coming in from this particular machine? What is the how do you actually know, right, that you're probably getting the data from here? Maybe you have a knob, you increase the RPM, you listen to the motor RPM increase, you assume that okay, somewhere there the motor is there. You go to max RPM, motor is struggling, it's making a lot of noise, you assume okay, motor is somewhere there, right? But you are depending on your sensors and actuators, right? So there's going to be some sensors and actuators, I mean, not actuators, but there are going to be sensors which are present inside here. And your assumption is that these sensors are getting you this data. So now my thesis, the thesis that I've been working on is, what if this can be made in a different way, right? So what if instead of having your sensors, your PMSM motor, and your dyno and all of these things, what if we can add one more layer to it, right? So let's say that we have another layer on top of it, right? So this layer is kind of sitting on top of it, and we are saying that this is basically my digital twin. Okay, so digital twin is a very fancy term to use, right? So what a digital twin basically means is that It's just going to be like something like this is at best like something which is a machine learning algorithm, right? So there is nothing else which is so fancy about it. It's a machine learning algorithm. Of course, our algorithms might be a little bit more accurate than any generic stuff, but it will be something which is much more accurate. Now, this digital twin, if it is also able to communicate with your control panel, right? For your student, does it really matter where they're getting the data from or how they are working with it? Think of it from an experience perspective first. Um, let's not talk about just a virtual laboratory, but just think of a physical lab. I'm giving you a motor dyno, and the motor dyno, instead of just collecting more data from the sensor, it is also able to collect data from a cloud, right? So this is basically a cloud. It is able to collect data from the cloud, and the cloud-based data is also presented on the same control panel. Assume that I'm telling the student that it is a cloud-based data, it is a digital twin data. Assume that the student is also notified about it, or we can say the student is not notified at all. My gut feeling is that the students will not be able to tell the difference about what exactly is the data coming from. Now, the more important question is, why would you want to do this, right? What is I mean, you spent 5 lakhs, 6 lakhs getting a motor dyno, then why do you want a digital twin there, right? So the answer to that question is, right, the moment you say that you have a digital twin, so what happens is, I can probably have 20 different types of motors, right? Nothing's going to stop me from doing it. You cannot purchase 20 motors. Can you purchase a 400 volt PMSM motor, right? Will it be possible for us to run a 400 volt PMSM motor in our laboratories? No, definitely not. The power supply alone for a 400 volt PMSM motor would probably, if you're looking at AC power supplies, right, it would probably run into 20-25 lakhs. Battery packs run into 15-20 lakhs. It's an extremely high voltage system, and you cannot allow your students to go even within 6 or 7 feet of this high voltage system. So such a dangerous one, we cannot put it into the college laboratories. But if all the cars are working on 300 volt, 400 volt systems, sports cars, commercial vehicles are all working on 800 volt system, how do we give experience to our students, right? Now, the same thing, we've probably invested, you've got a 2 kilowatt PMSM motor. Will you run with a 2 kilowatt PMSM motor throughout the entire life of the lab? Should every student do the same experiment, get the same data, do the same kind of presentations? I mean, think about it, right? So whereas now what we can do is we can give you 20 different types of motors, right? We can probably give you 7 or 8 different gear ratios, right? Single speed gear ratios, we can probably give you that. And let's probably assume that every single motor here can work with 3 voltage ranges, right? So maybe let's say a 36 volt, 48 volt, and 60 volt. You can run it at 3 different voltage ranges. You allow the students to probably do the calculations, figure out what is happening. So what is the total number of experiments that you're looking at here, right? With one single set of equipment, 20 into 7 into 3, right? That's about 420 discrete setups that are possible. You get the idea, right? So this is basically where the digital twin comes in, right? It can either replace it completely if it is a virtual setting, or it can kind of add on to your existing lab equipments. I'll show you some of the things that we have with this, right? And most importantly, you can allow them to experiment with, right? Experiment with. Nothing's going to happen. You can tell them, run the motor towards max RPM, run it and find out what happens to the temperature. You're not going to blow the motor, right? You want to run a 36 volt motor on a 400 volt power supply, right? You want to understand what happens, allow them to go do it. I mean, that's how you learn, right? You do something and you learn. So you start setting up your question papers, which would kind of revolve around this. So let me kind of like, enough with talking. I know like I've been talking. So this is a sample that we have built. It's at motor.labonwheels.in. So this is a sample front end that we have built, right? So Imagine that this front end that you're looking at right now, imagine that is sitting on your equipments, right? You have a TFT LCD monitor, and this is sitting on the monitor in front of you. Okay, this is motor.labonwheels.in. I'm not sure if I can post it in the chat window here, but this is motor.labonwheels.in, right? So that's where I am. So now I can probably start my experiments. Um, I can probably, start setting up some motor speeds, right? And I mean, the control what has been implemented here is a very simple PD controller. So it's going to have a lot of torque ripples that you can see here, right? But actual, units would probably have much more, better stuff at this, right? So this is just something to show you. And, you can run it at various different speeds. You can also set up some external loads. There's a constant load, so how do we do it? Okay, maybe I can set up 2 Newton meters of load. So the moment I set up load, current is gonna rise. Yeah, okay, current is rising because it's now working against 2 Newton meters load. So there's about 3.54 Newton meters is what it is providing. I can also probably make it run a oscillating load. I'm not sure if this works yet. It's still under, you know. So this is a sinusoidal load. So my control system is absolutely not set for it. So that's kind of why this is happening, right? It's maxed out. I think the motor is maxed out. The motors come to a standstill. It's a full load condition. It's stalled. So current is 40 amps, right? 40 amps, and I think this is 48 volts. So 15 to 4200. I mean, yeah, it's almost at its max, right? So you can test it here. So this is 45 amps is the max current, and you're at 44.3, and your motor is no longer running. This is a 2000-watt system. PMSM motor, right? A BLDC motor. So I can add some more motors, probably all the 40 different motors that I want to have. I can have all of those things coming in here. And the idea is now once I've kind of removed my learning outcomes from the actual equipment. Now, why do I still want the actual equipment? Because students will not get a feel for it. If you want the students to have a feel for it, you cannot give a basic front end like this. They'll need to be able to see, touch and feel and things like that. So probably like, we'll replace this speed control with a dial. So these dials can actually be replaced with actual dials. We can spoof, right? I mean, for all practical purposes, I can build it so that you don't even need a TFT LCD here. You can still use the same cloud-based data here as well, right? It would still work the same. We have kind of come to a point where we can still make it happen, right? So now what ends up happening is, imagine the kind of learning outcomes your student has, right? So 420 different discrete experiment setups, which means instead of having a generic lab exam, you can tell them, I'm trying to develop a small commercial vehicle. What is the best possible motor and gearbox for it? The students will go experiment with it. They'll try multiple combinations. They'll come up with whatever best solution is. You have 300 people in your class. Every single 300 person can do a different set of experiments. They can rotate the experiments. You increase the longevity of it, right? And most importantly, now you are no longer working with just a PMSM motor and a dyno, but I am kind of offering you an option on the cloud, right? Not on the real system, but on the cloud, I'm offering you an option to also work with motor control, right? So maybe rudimentary, it's not as accurate as probably modeling it with MATLAB Simulink or something. We've not reached that point. There's been no reason, but we can do it if needed, right? So I'm also offering you an option to do some kind of motor control, develop some algorithms, check how a simple PD algorithm might look, PI algorithm might look. You can kind of play around with all of these things, right? So this is basically the thesis that we have. So if you want to kind of increase the learning outputs, if you want to increase the learning outcomes, if you want to kind of make it interesting for the students to learn, instead of giving them experiments, we should replace it with some kind of problem statements. So which again we kind of been doing it for quite some time for some of the institutions. So we can prepare a set of 50 100 different problem statements, and you can ask your students to work with it. Now, this is purely on the sheer amount of experiments that you can offer, and how many different experiments the students work with. This is purely on numbers. Now, on the other side, this can also come in very much in handy when you're looking at it from a cost perspective. Okay, so why cost? So let me kind of like just show you the second thing which we have. So from a cost perspective, right? So time and material, both of it is equal to cost, right? So this is basically how the engineering industry works. We work on a man and material, which is time and material kind of a cost. And to kind of give perspective to things, India being a low cost development center, we call it as LCC, right? So the LCC rates are about $15 per hour, right? This is kind of how things were until our um, the recent tariff wars and things started. But until then, $15 an hour is the bare minimum that you would do. And if you are looking at building some AI ML solution, this can go up to 70, $80 an hour, right? So this is kind of on the higher end. So yeah, so what I'm trying to tell you is time is also money, which basically means if you want to do some kind of meaningful battery-based experiments, right? Um, I mean, let's take a very simple battery characterization equipment. You have to charge and you'll have to discharge at point 0.1 C, which probably means that you're probably gonna be sitting all day to kind of run one charge and discharge cycle and to get the data from that. Now, how many such cycles do you need to do before you can evaluate SOH? Around 2000 cycles. So even if you're able to cram it into 2 cycles in a day, you are looking at nothing less than 3 years, 4 years to come up with data of your own to basically start working on SOH. So now my question to you is it really worth it? Think about it from two different perspectives, research as well as the student learning perspectives. I would say that we as a country, India as a country, we are 20 years behind the Chinese when it comes to anything on EV technology. So the Chinese have kind of leapfrogged us. They've gone way, way, way more advanced than even Tesla's, which is why Tesla uses blade batteries now. So when this is the industry scenario, does it really make sense for us to sit and try to put up some basic battery testing equipment and hope that we will come up with data or I don't know whatever it is, right? I mean, it's basically a catching up game, and it's not going to help us produce any meaningful research or some things like that. I mean, that's my take on it. I'm not against doing it, but it's my take on it, right? So unless otherwise you're doing some metallurgy or something like that, for an undergraduate kind of a setup, having a battery charge and discharge equipment is probably at best not going to work out, right? At least not in a traditional sense. So what can you do for it, right? So this is why we built again another battery simulator. This is again hosted at battery.labonwheels.in, right? So this again a trial version which we have. So here what we try to do is we try to address two different, I mean, the primary problem with batteries, right, which is cost. And second thing is we also try to address safety, right? So you cannot safely discharge a battery at 10C rates. Try doing it. If your lithium battery catches fire in a lab, people are gonna panic, right? And if you don't have proper equipments on hand, you're not gonna be able to control it as well, right? So you have that problem. So what we do is we give you an opportunity to basically work with this in a very simple manner, right? So again, this is web-based, but you don't have to think, oh, it is web-based. Why does it actually matter to us? We want to have something better, right? Don't disregard this just because it's on a web. It is on web, because right now we are just like running it, for a POC. But this can very much be okay. This experiment is not online, so let me just go back and try a different one. Give me a second. I mean, it's still very much under development, right? So okay, I think the backend servers are a bit down, but that's okay. So let me go take a lithium ion phosphate battery, and let me try to do a battery characterization for it, right? So I'm gonna want to run it at 3C rates, right? Which is 3C here, right? 3C here. And I'm trying to run it at slightly higher temperatures, 30 or maybe let's say 45 degrees, which is not exactly recommended, but let's try to run it at that, right? So now let me go run the experiment. So now a real experiment of this nature, you should have a temperature chamber, right? And even at 3C rates, 20 minutes, whatever problem that you're going to have, in case the battery catches fire or whatever it is, you'll need to have fire extinguishing equipment. You'll need to have trained personnel present. There's a lot of things which you need to have. But here, nothing of that sort. Okay, I think because the server is down, this particular server is down, it might be, yeah. Let me probably, it might not have the mock data for it. Let me kind of run it at normal temperatures. Let me just show you how it works. It perfectly works with the other temperature ranges as well, but let me just show you how this whole thing works. Um, yeah, so what it's going to do is it's going to, I mean, we have roughly about 5.5 lines of code which is driving this logic. So these are not lookup tables that we have, but we rather have some state-of-the-art machine learning algorithms which are running here. So these algorithms would help us calculate how the battery would behave at a cell level for each C rate against, okay, I'm sorry about it, right? So the server is down. Unfortunately, I don't have access to the backend server. My CI/CD team, it's 8:50, so it's better not to wake them up in the night, right? So let me probably skip out on this, but this basically will get you your cell characterization, which is how does your voltage vary with respect to time, how does your SOC vary with respect to time, how does the temperature changes, right? And not just that, right? So remember I was talking to you about money, right? The amount of money that you would invest. So just look at the kind of experiments that you're able to do, right? So we have options for doing battery aging study, something which would actually take you about 7-8 years to basically perform. Because of our ML algorithms and digital twin, you can now run it over a period of 1 month, right? So advanced studies, sit down, do that, figure out how it's going to work. We also have some electrochemical spectroscopy, right? So you can run some internal resistance, internal impedance spectroscopy experiments. I am told that this particular experimental setup is something which would cost you about 1.5 to 2 crores, right? So instead of spending so much setting up an equipment, not having a proper return on investment, what if you could have the same kind of a data coming out without having the actual experiments? I mean, without having the actual equipment. So now the fidelity of the data, right? How accurate the data is going to be, how good it is going to be, right? So at least for the battery, we have white papers which kind of like prove that these algorithms are about 70-80% as accurate as any commercially available battery modeling tools. So this would include all your COMSOL, your MESIM, your GD suite. So this is about almost up to 70% accurate as those systems. Now compare it on the cost. A GD suite license, I don't know, probably about 30 lakhs a year or something, right? So do you need so much of firepower to do it, or does this work out, right? So this is basically how we've been thinking about it, right? So now I guess I can get back to here and I can probably finish off what I started. So now when I say that, the problem is with higher order thinking skills. The problem is with how we've been able to offer learning. The problem is with how we've ourselves been kind of like not allowing the students to experiment, I think this is something which your digital twins can solve. Now, what exactly are digital twins? I mean, this is a very fancy word. Forget digital twins. A digital twin is a fancy word for a machine learning algorithm, right? Of course, this algorithm has to be built to industry standards. We'll need to have proper infrastructure, front end and back end. So it's there, right? It's there, but it's just machine learning algorithms. You can say that this also has reinforcement learnings, right? So what I mean by that is, in a traditional sense, a digital twin is supposed to learn from real systems, right? You have a machine learning algorithm, you have a real system. These are supposed to be talking continuously. So in that way, if you look at it, this is not technically a digital twin, but you can still call it, because the inputs to this still goes from the motor, right? So the user sets the RPM, the user sets the torque needed, all of those things using physical inputs on the dyno. So which means those inputs do go to the digital twin, and the digital twin computes what the output has to be, and it gets you the output. The motor will still run, it'll still like increase its RPM, it'll still lower its RPM, all of those things will happen, but it still like, kind of works on this way. Okay, so that's basically what work we've been doing on, right? That's basically how we have kind of tried to integrate this. And we've also tried to like, I mean, because the other thing, if you remember, I said there's a lot of focus which needs to be done on um, yeah, industry techniques and process, right? So how we kind of like handle both of it with this particular virtual integration is like this. So now we would probably offer a problem statement, like let's say that you have a third semester student who comes in and he needs to know about what model to select, right, for a particular application. So the problem statement might look something like this. I mean, just a sample statement here, right? Just a sample statement. I would probably say your job is to select a motor suitable for equipping our new electric small commercial vehicle, right? Ensure all proper process are followed and documentations are done, right? So this is how my problem statement to him is going to be, right? I'm not going to tell him, hey, go run some experiments on BLDC versus PMSM and tell me. I'm just going to leave it open-ended. I'm going to tell him, we need a small electric commercial vehicle, and how are you going to do that, right? So which basically means now the user, I mean, let me just pull this up here, right? So I mean, you would probably be seeing this a lot of times. Let me model design, coding. Let me say we model PDLC, right? Images. Okay, everything is about coding. Yeah, okay. Let's kind of, okay. This is probably better. Copy image and go here, right? So now what the student is going to do is, let's say this is for 30 marks. So I'm going to give him maybe like, I mean, he's definitely not going to be doing detailed design and all. He's just going to do high level design, maybe system design and high level design. That's all that he's going to be doing. So these three steps, I would probably give him 5 marks for this, 15 marks, 5 each for these things, probably for a total of 30 marks, right? So your rubric can be something similar to that. So now what this particular person is supposed to do, right, is to now probably he will start with requirements gathering, right? So we would probably give him a lot of text, which would contain voice of customers. And the first task he does is convert VOC into requirements, right? Convert requirements into specifications. How do you do it? Maybe do some rudimentary math modeling. So this is going to teach him some MATLAB, Simulink, Python, whatever he wants to use. Do some mathematical modeling. And once he does it, he has to come up with a system design. Then he moves on to a high-level design where he's thinking, should I use a BLDC, right? Or should I use a PMSM? should I use 2x motors, or should I use 4x? I mean, four motors, single motor, that kind of combination. And then he now comes to your, I mean, this is all before he comes on to your dyno, right? So now at this point, he comes on to your digital twin dyno, and now he's kind of like he needs to have all of these equipments, right? So he needs to have access to these things. We'll ensure that it is there. So he comes to the dyno, he collects data, right? He goes back, and then he probably does some data crunching on it. I'll probably take the questions just in 5 minutes. Let me just finish it and take the questions. So data crunching happens, right? And he has to prepare reports as per industry requirements, right? So now what happens is he's not just doing an experiment in the lab about like motor testing, but he's rather been doing the top left of the V model. So now imagine this particular person goes to the industry, and he's sitting for his placements or something like that, and he says that, hey, I've done this exercise, not just this one exercise. I've done a whole lot of things on this line, right? I've done it for motors, I've done it for controllers. We've even done wiring harness. We've done some physical testing. We've done some MIL, HAL, SAL. These are all things which you could kind of integrate into your digital platform, right? And when your questions kind of convert from being lab experiments into something of this sort, I know it takes time, but when you look at it from a student outcome, when you look at it from a placement perspective, um, if you can just tackle 3 or 4 different industry process every single year, right? Maybe 2 every semester if you're able to tackle. I'm pretty sure that there is going to be um, nothing called as a skill gap by the time they're done with it, right? We are able to do it over a period of 15 days, 20 days training, intensive training. We are able to tackle it. If 20 days can do that, I'm definitely sure semesters 3, 4, 5, and 6 should be more than sufficient for us to tackle these things, right? So with that, I will probably stop talking about this, and let me probably open it up for questions, right? So hope that's okay.
Yeah. Thank you so much, sir. Uh, yeah. So, dear participants, if you have any questions, please raise your hand, and also you can write your questions in the question answer sessions. Yeah. So, Nathia, yes, you can ask the questions. Okay. We have also got the questions from participants in the question answer sessions. So just let me read out one by one.
I can do that as well. So
Okay.
2028 is the earliest, right? Okay, so let me probably go ahead. Mr. Satyajit Sahu,
Yeah.
could you elaborate on how this virtual physical integration is practically implemented? Um, Okay, so practical implementation, like I showed you, the backend we run some Rust or Python code. The front end is usually built on TypeScript if it is for a web-based front end, or we can also do it with embedded systems as front end. So I think we are now at a point where embedded systems can very well talk to the cloud-based backends. We have TCP/IP connections, so we can make the front end either physical. If you want real gauges, real switches, and knobs, we can do that. In which case, we would probably be going with embedded C or MicroPython or something like that. A web-based one still remains TypeScript or something, React or something like that. Okay. Hope I answered that question. So, do we have any EV practicals in any VLab or national? So, if you're talking about VLabs, the Government of India thing, I'm not sure. I did see something from Amrita, which was there, but I'm not aware of that, right? So, I'm unfortunately not aware of it right now. Yeah, the same question again. So, Considering the integration, okay, this is the same thing. Okay, considering the integration of virtual and physical components, how do you measure the effectiveness of this educational approach, and what data points or metrics do you track or monitor student? Okay, so what we do is, I mean, so this question is more valid. I think the next question, so pedagogical advantages and limitations. So I'll probably combine these two things. So traditional evaluation metrics, when you say you have rubrics and stuff, so that is kind of something which is traditionally been made for question and answers, multiple choice questions. It's been for something of that sort. So the moment you bring an open-ended question, right? Assume that you have an open book exam. So you have an open-ended question which comes in. So then the metrics are much more easier. So there is no single right or wrong. So your rubric can just be about, was the process followed? Was the thought process visible? Did the users take pains to plot it? Did he kind of observe any anomalies? Now there's a virtual platform, which means I can deliberately include some kind of like problems in the motor, right? One particular RPM band, I can reduce the torque of the motor. So you cannot talk anything about this to the student. You allow the students to go work on it, and then you find out if he's actually found it, right? So maybe once you do it, next batch they'll know. So the next batch you don't include it. So next batch will go search for it. It might not be there. For another batch, it could be some efficiency problem. So we can kind of play around with all of these things, which kind of opens up a totally new way of looking at education. So we don't look at it from an academic perspective. We start looking at it from an industry perspective. So now me as a manager, engineering manager, how would I evaluate my fresh graduates' work, right? So suppose I have a batch of people coming in, GETs or something like that. How would I evaluate them? I'm not going to use the same rubrics as what a college might use. I'm going to see how long did you take? Was a solution actually effective? Did you meet all the requirements I had? Did you prepare the documentation properly? Did you kind of like present it well? So your rubrics can basically change. So now, since your whole idea is to kind of like meet industry norms, industry requirements, I think this provides an opportunity for you to do that. On the same lines, if you think I don't want to do any of this, I want to integrate it with my LMS, with my regular platform, I don't want to rock the boat, I just want to use the same experiments as how I'm using, can I still use the physical, I mean the digital labs? I mean, it will more than enough work, right? You can do that as well. So I think that kind of like should answer both the questions there, right? Thank you for that. um, So the others who have hands raised, how do I handle that? So can you unmute them, or I think you're on mute. I can't hear you.
Yeah, sorry. Actually, I have already given the co-host to him,
Okay.
so maybe they will ask the question. They can unmute themselves, and they can ask the questions. If also they can ask the questions in the question answer box. Yeah, Arun Kumar sir and Nathia ma'am. If you have any questions, please unmute your mic and please ask the questions. Okay. So I just got the one questions in my WhatsApp group.
Right.
Uh, uh, okay. Do we have any EV practicals available in any VLab on national or international platform?
So that I'm not aware of.
Okay.
So I can probably check right now, but I'm not aware of um, anything on electric vehicles per se. There is too much of information here, so I'm not able to go through it. But
Okay.
I think you can go search for it. It should be possible.
Uh, sir, thank you so much, sir. So uh, we are very thankful to Mr. Sajeeth Kumar, head of R&D at EV Skill Lab, SkySkill Lab, for sharing his valuable thoughts on Twin Lane Laboratories. and transforming maybe engineering education through these online mode platform. Right. So we hope that the today's two sessions have truly enriched your knowledge, and I and also we assure you that we will continue the same spirit of innovation and learning in the upcoming session. Right. So thank you so much.
Thank you.
Uh,
Thanks for giving the opportunity. Hope I was able to convey my thoughts on it. So thanks a lot for having me
And
here. Have a
yeah,
nice.
we also hope that the participants got better knowledge from these two sessions. So so with that we formally concluded this session too. Thank you so much. So thank you so
Thank
much.
you.
Thank you also all
Thank
of you.
you.
Thank you.
Good night. Bye bye.
Bye bye. Good night.